All right, good morning, class. Sorry I'm not going to be there today. I'm busy doing Kansas math assessment downstairs. Today we're going to be working on the back side of our Maclaurin series, but before we get started, I've got a guest speaker for you.
Thank you, Mr. Flynn. It is a pleasure to be here. Calculus students, I met your teacher 8 years ago at the White House where we were honoring the great math and science teachers from our 50 states. Just Google Presidential Awards for Excellence in Teaching Mathematics and Science for the year 2013. From the moment I met Mr. Flynn, I knew I wanted to see him teach math. So this is a dream come true for me. Mr. Flynn, what will we be doing today?
Okay, well, Mr. Obama, it was great meeting you also. So today we're going to be reversing what we're doing, and we're going to try to come up with the original series that gave us this. Like on the first page that we did, we were given a series, we had to come up with these terms. Now we're going to reverse it. We're given the terms, and we've got to come up with what the series is.
That sounds amazing. Let's get to it.
Okay, so the first thing we want to pay attention to is the factorials. The factorials, I don't care to give the feedback. The factorials tell us everything. Now, looking at this, we've got these factorials, right? In fact, we could probably say that this is over 1 factorial and over 0 factorial. And there's only one known sequence that has all the factorials, and that is e to the x. So I'm going to write out the first couple terms of this. Now, if I'm looking at this, looking at these different terms, I'll notice that the 3 factorial here has an x to the 5th in it, whereas the 3 factorial here has an x to the 3rd. So it's like our exponent should be 2 larger. And in fact, if I look before it, the 2nd factorial is below an x to the 4th, whereas the 2nd factorial here is below an x squared. So I think if I were to multiply by x squared, that means we're dealing with x squared e to the x. And if I distribute my x squared all the way across, I'll notice that we now have what we're looking for. So now the next thing we have to do is actually write the Taylor series for this, the summation notation. So I'm looking at this, and I think I might start with n equals 0, because what that does is that allows the term number to match the factorial and also to match the exponent. So I can say sum from n equals 0 to infinity. The denominator is going to be n factorial. The numerator, right? I think it matches the factorial, but it definitely doesn't match the. Boy, I really had some bad stuff here. This should be a 4th power, shouldn't it? Jeez, that's terrible. Sorry, Mr. Obama. If I look at these powers of x, right, these x powers, they all differ by 1, so I know it's going to be a 1n, or just n. But again, when n is a 3, and if I plug that 3 in for here, I'm going to get x to the 3rd. But really, I need x to the 5th. It's like I need to add 2 to there to get there. Let me try this one. If I plug a 2 in, right? And I plug that 2 directly into my exponent here. 2 plus 2 is 4. Sure enough, we have x to the 4th. If I try my n equals 1 and I plug a 1 in for it, 1 plus 2 is 3. Sure enough, we have x to the 3rd. So there is our Taylor polynomial in summation notation. Let's move on to one more, and I'll let you kind of spend the rest of the hour working these out. Okay, so again, remember, the factorial tells us everything. And I believe, oh, also, when I'm looking at these crazy numbers here, I think we would all agree that 27 is really 3 to the third. 243 is really 3 to the fifth. 2187 is really 3 to the seventh. Now you might wonder, why did I think of powers of 3? Well, I noticed that the first term was a 3 and the second term was a 27, and I'm like, hey, those are powers of 3. I wonder if that works everywhere else. Sure enough, it did. Well, the only one we know that has these odd factorials is the sine one, right? So if I think about sine of x, I'm going to have the first couple terms for this. You'll notice that we pretty much match up completely. The only thing that we differ by are these numbers, right? Well, what if instead of sine of x, we did sine of 3x? Well, that would be, whoops, that would be 3x. Okay, I'm going to leave some blanks here for a second so I can write this out quicker. Yeah, if we place a 3x in for the x, it will match up lovely. And I got to figure out how to write the formula for it. So again, I'm just going to start off with a 0 again. And the reason why is that I notice this is an alternating series, right? Do you see this alternating business? And I notice that we're negative anytime we're an odd term. So I can just say -1 to the n, and that would take care of the alternating portion. Now, the denominator, I notice that these factorials differ by 2. So I'm going to say 2n, but then I need to do a little bit of adjusting, right? So let's try out this 3. If I plug a 3 in, 2 times 3 is 6, but I need 7. So I'll just add 1 to that to make it work out. If I try out with the second term, 2 times 2 is 4, plus 1 is 5, so that works out. And you'll notice that these exponents here, right, are the same as the factorials. So I can just copy down what we did for the factorial. And that's how we do this. Remember, the answers are located on, I think I put them on either Google Classroom or the, yeah, I think it's on Google Classroom. Well, Mr. Obama, what did you think of all that?
Class, let me just say thank you for allowing me to learn side by side with you. And Jackson, keep putting out those videos on Cody. They are Riz-tastic.
All right. Well, you heard the man. Thank you all very much, and I will see you on Monday.